As we're going to go through the quantitative review for our Foundations in Physics quantitative tests. There are both quantitative and qualitative questions in here. Please remember that you can slow this down or speed it up to meet your needs. You can check all your answers or just the ones that you're not feeling as comfortable with. And we need to get ready for a test next class. Number 1 says, give a written description to the motion. There are 3 really important things here from our position versus time graph that they give us. The 3 most important things is that if the starting position is 0, the overall direction is it's moving in a positive direction, and the object is slowing down. And we know that because the slope becomes less steep as time goes on. If we wanted to give a rock star awesome answer, we might want to look at something like this. The object started at a position of 0 meters. It moved in a positive direction while slowing to a stop 10 seconds later, and we can find out here that the total distance it traveled was 40 meters across those 10 seconds. Draw a motion map for the object, which include velocity vectors. Taking a look at this, officially we should actually have 11 dots, but there just wasn't space, so our starting position was here. That would have been at 0. Notice the distance between the dots get closer and closer together because it's slowing down. The blue velocity vectors are getting shorter because it's slowing down, and the acceleration vectors are all in a negative direction because this would, if you've got a decreasing positive velocity, that's going to be a negative acceleration. So the acceleration vectors, the red ones, should all be the same size and in the opposite direction. Explain how you can determine the instantaneous velocity at 2 seconds. We did this using slopes of tangent lines. I've used this orange tangent line listed at 2 seconds here. If we were to calculate the slope of the tangent line at 2 seconds, that would give us the instantaneous velocity at 2 seconds. Assume the initial velocity was 50 meters per second to determine the acceleration of the object. To do that, we need to realize what we have. That it's 50 meters per second. We know that the change in time is 10 seconds, and we know it slows to a stop. So our final velocity is 0 meters per second. And this probably would have been better had I put these over here as given information, and that's obviously in addition to the initial velocity of 50 meters per second. So how do you find the acceleration? We want to look at the slope of a velocity versus time graph as acceleration. To do this, we want the final velocity minus the initial velocity divided by our change in time. In this case, our final velocity was 0 meters per second because it slowed to a stop. Our starting velocity was given at 50 meters per second, and that happened over the course of 10 seconds, in which case we end up with a negative 50 meters per second divided by 10 seconds, which is negative 5 meters per second squared. Because I have these equal signs all in here, that's saying the acceleration is negative 5 meters per second squared. That negative sign is super important. It says Pontiac Trans Am, that's a kind of car, was at rest and accelerated at a constant rate of 4 meters per second for 6 seconds. How fast will the car be traveling? So you might want to write down the given information. Acceleration, 4 meters per second squared. It was at rest, so the starting velocity is 0 meters per second. 6 seconds is a clock reading, a final clock reading, or a change in time. And do we know anything else? They want us to find the final velocity. Practicing which units go with which variables is super important. To do this, we need to start with a general equation. We can start with final velocity equals the acceleration times the clock reading plus the velocity at time 0. We know the rate of acceleration for this problem is 4 meters per second squared times our clock reading of 6 seconds plus our initial velocity. It was at rest, so we can add 0 meters per second here, or if you want, you can leave that out. 4 times 6 is 24. A meter per second times seconds. This seconds is going to cancel out with one of those, so we end up with meters per second, and those are the appropriate units for the velocity. So this would be the velocity final, or you could have also said the velocity at 6 seconds. I don't know why that's not right. So velocity at 6 seconds. So moving on. So a tailback, that's a football player, is running with a velocity of 5 meters per second. When a defensive player grabbed onto him, dragged him, slowing him to a stop in 4 seconds, how far did we travel? So we're trying to find displacement. So we have a starting velocity of 5 meters per second. Slowed him to a stop. We have a change in time of 4 seconds. And we need to find the displacement. So with this information, it might be helpful for us to sketch out a velocity versus time graph. We have velocity in time measured in seconds, velocity in meters per second. Our starting velocity was 5 meters per second. It slowed to a stop, and we said the final clock reading is 4 seconds. And we happen to know that the area under the graph, the area of this triangle, is the displacement. So to do this, we can say that the area of a triangle is 1/2 height times base. In this case, the displacement is equal to 1/2. The height of this triangle happens to be the velocity at time 0. The base is our change in time. And so our displacement is 1/2. The starting velocity is 5 meters per second times our change in time, which was 4 seconds. And so quick math. 1/2 of 4 is 2. 2 times 5 is 10. And meters per second, so the seconds cancel out, and we end up with meters. 10 meters is our displacement. And that finishes up side 1 for us. Moving on to side 2. We have stacks of graphs. In these cases, we can use 2 sets of tools. You'll want to think about slopes of tangent lines in our ABCs. For the first graph, the slope of the tangent line at time 0 is 0, so we want to have a y-intercept this way. If we get our ABCs, this is a slope that's getting steeper, so it's an increasing, it's tilted up, so it's positive, so an increasing positive velocity. So we're going to have our ABCs are going to look like, going to build a velocity versus time graph for that. Because we can do our ABCs for our velocity versus time graph, this slope is constant. It's tilted up, so it's positive, and we know the slope of any velocity versus time graph is acceleration. Constant positive acceleration, so our acceleration versus time graph looks like this. Going on, if we get a motion map, we want to start at rest. Dots get further apart. Velocity vector, nothing at the beginning, and then a larger and larger velocity vector. And the acceleration vector should all be positive. You guys have the answers to this out on other worksheets, but a quick sketch of this. Again, with the slope of the tangent line at time 0 is this. We'd have a small negative slope and a bigger negative slope, so we should have this. But checking on our ABCs, this is an increasing slope because it's getting steeper. It's tilted down, so it's negative, and we know the slope of any position versus time graph is velocity, so an increasing negative velocity, and that matches up there. Let's do our ABCs for the velocity versus time graph. Constant, negative slope, so that's a constant negative acceleration. A constant negative acceleration, so our line's going to have to be below the time axis. Moving on, shape of the graph, we start with a big positive slope, so we start with a big positive velocity. We have a decreasing positive slope, so that's a decreasing positive velocity. We get this. We have a constant negative slope as it's tilted down. A constant negative slope is a constant negative acceleration, and we're here. Next graph, slope of the tangent line, we start with a big negative slope, so we start with a big negative velocity. Our ABCs, the slope is becoming less steep, right? It's becoming more flat, so that's a decreasing slope. It's tilted down, so it's negative. So a decreasing negative velocity, so a smaller and smaller negative velocity approaching the velocity of 0. We do our ABCs for the velocity versus time graph. It's a straight line, so it's constant. It's tilted up, so it's positive. A constant positive acceleration, and we're above the time axis. I don't have time to do motion maps. Well, we'll do one of these. We did the third one in class the other day, so how about if I do number 2? It starts in a big positive position. Because it's speeding up, the dots get further away from each other. The velocity vectors get longer and longer. The acceleration vectors have to be negative because it's a constant negative acceleration. And all these red acceleration vectors should be the same length. Moving on. We did these in class today. So it says, consider the graph at the right. At what points is the object going most slowly? Well, you want to look for where the slope is flat, right? B, it's flat. F, it's flat. So the best answer, it's stopped or going slowest at B and F because the slope is flat. Number next, we've got over which points is the object speeding up, and how do you know? Well, we're going to want to find places where the slope is getting steeper. Well, if at B we're stopped, right after that we're moving a little, so the velocity had to have changed. So we're looking for spots like B, where the line is flat, and then we have a bigger and bigger slope. So from B to C, and the other place is from F to G, the slope is getting steeper as well. Moving on, over which intervals is the object slowing down? So we're going to look not for where it's getting steeper, but for where it becomes less steep. We say A, B, and E, F. So we're going to go over to a red slope. So from A to B, the slope is becoming less steep. It's becoming flat. And E to F, it starts in a big negative slope, a smaller negative slope, and starts out flat. There's actually two other places where it becomes less steep. From G to the end of the graph, the slope is getting steeper. And actually from time 0 to point A, the slope is actually becoming less steep as well. Over what points is the object changing direction? Well, for it to change direction, it would have to have a positive velocity on one side and a negative velocity on the other. So places where the slope changes direction, it's a positive slope before B and a negative slope after B. Or for point F, it's got a negative slope before F and a positive slope after F. So anytime the slope changes direction, the object is changing direction as well. So we already did that one. Over what intervals does the object appear to be traveling at a constant speed, and how do you know? Well, a constant speed or constant velocity would have a constant slope, in which case the slope is only constant from point C to point E. So through C, D, and E, the speed is constant because the slope is constant. I'm going to have to end this at this point and put a second video for the remaining of the review.